Welcome back to the second video on dynamics of uniform circular motion. Another example that I found when I was online, I saw this is a trick to get the glue out of a glue bottle. And it said to use the centrifugal force to get the glue out of the glue bottle. Well, I mean, you are using the centrifugal motion of the glue to get it out of the bottle. See how the guy is holding the glue bottle so that the nozzle is on the outside of the circle. And if he swings his arm around like that, well, the glue doesn't want to do the circle, and it's liquid, so it doesn't necessarily have to move in the circle exactly the way the plastic does. So you're going to see that the glue is going to start making its way to the outside of the circle. So some would say that's a centrifugal force. Me personally, I would say that's the glue just trying to go in a straight line at all times and ending up sliding out farther from the center of the circle, which would be his shoulder. So before we go, just a couple of quick examples, and I'd like you to listen to this, and then I'd like you to stop the video, give it a try, and start again and see how you can do. This is one of our focus on concept questions. It says a small cylinder rests on a circular turntable that is rotating clockwise at a constant speed. The cylinder is at a distance of 12 centimeters from the center of the turntable. The coefficient of static friction between the bottom of the cylinder and the surface of the turntable is 0.45. What's the maximum speed that the cylinder can have without slipping off the turntable? Now, the force that's going to make this happen, make this circle happen for the cylinder, is going to be the static friction. I know there's motion going on here, but there's no relative motion between the turntable and the cylinder. So this is going to be the static friction. Now, we're looking for the maximum speed, so we're going to need maximum force. So I'm going to say this is going to be maximum static friction, which is good because I have an equation for that. I want you to turn off the video for a second, pause the video, and see if you can come up with the maximum speed given the coefficient, the radius, and so forth. Before you do go, a hint, maybe draw a free body diagram of it, and I think maybe some things will fall into place for you. Okay, pause the video now. Okay, and we're back. Now, what I did is I made a free body diagram of this cylinder, and so this is going to be like for an observer that's maybe right there, looking this way. The velocity is going away from you. That's what I mean over here with the velocity as the x. The centripetal force is going to be towards center, of course, like they always are. It's friction, and that center is going to be on your right as you're looking. Normal force will be straight up into the air, force of gravity straight down into the ground. So here we go. By the way, these two are going to be the same size. The maximum static friction is probably going to be less. It is going to be less because you could see that the coefficient is less than 1. Now, the centripetal force, like any net force, is equal to mass times acceleration. And so it's going to be the mass times the velocity squared over the radius. Now, the centripetal force in this case is just the one force in the x direction, the force of static friction. If there was another force acting backwards like that, there isn't, but if there were, then I would subtract off that other force. There's not one here, so we'll just get rid of those. They're equal to mv squared over r. Now, again, centripetal acceleration is v squared over r, back from kinematics. All right, so the maximum static friction is going to be the coefficient of friction times the normal force, and since we're on a flat surface, normal force and force of gravity, mg, are the same size. So now I canceled out the masses and I solved for the velocity, and I ended up getting a velocity of 0.73 meters per second. I hope you did too. Now, on my other example for this video, I have focus on concept number 7. See what we have here. We have two stones, identical, same masses, right? And they're being rolled on a tabletop, so I guess we're looking down on them. It says the radius of the larger circle is twice the smaller circle. So I've got radius 1, I've got radius 2, and radius 1 is 2 times as big as radius 2. It says, how's the tension T1, that'd be the one over here in this string, related to the tension 2, that's be the one over here. Now, I think you should draw a free body diagram for each. They're not super complicated, but I think you should draw a free body diagram for each. They're not mentioning anything about friction here, so don't worry about the friction. And let's see if we can get an expression for T1 in terms of T2. Okay? Shut off the video, give it a try. All right, everybody, I hope you got an answer to that. So what I did is to draw the free body diagram, I just thought I would just draw it right on the picture. I was thinking, well, for the same velocity, this small circle is going to have a very short amount of time. Careful, don't confuse the T for the period that I'm using, and the T for the tension. So I'll just write time out like that. This one over here is a way larger circle with the same velocity. It's going to take longer, bigger time, right? So my point is, you have to go all the way. The force has to be enough on the right in a very short amount of time to be able to go through all of those different velocities, 360 degrees around, versus on the left, it has much longer time to do that. So to me, I think it's a harder thing for the to do path 2 than it is to do path 1. So because of that, I drew the tension 2 longer and I drew the tension 1 smaller. Maybe I'm right on that, maybe I'm wrong. Let's see. So now either way, I do know that the centripetal force is a mass times the centripetal acceleration. So the only centripetal force on each is the tension. So you can see I have tension is equal to the mass times the v squared over r. Now, they said that the velocities were the same, so solve them for the velocities, and so I actually solve them for velocity squared, but if the velocities are the same, the velocity squares are the same too. So then what I did is I set those equal to each other here, and now I'll have masses canceling out like this, and the radii though. It said that the radius 1 is twice the radius 2, so how about I go T1 to R1 equals T2 R2. R2 over here. Now those R2s will cancel out, and you can see what I've shown. I've shown that T1 times 2 is equal to T2. So T1 is only half of what T2 is. So yeah, I don't want to say I told you so, but I did tell you so that the T1 is less, it's easier to go around that bigger circle in the same amount of time. I hope you got that same answer. So just to finish it off then, how do monkeys make their burgers? Well, on the grilla. See you next time.